In this final segment of Lecture 14, we're going to look at how to deal with some more examples, which you can then try out on your own. So, we're going to take a quick look at the second order parallel RLC circuit. And for this circuit, when you solve it, you're going to want IS of t to equal 10 times the cosine of pi over 6 plus 3 pi times t, where in this case we finally have radians and radians. In which case we can simply use radians to be what we end up looking at. For this circuit, the resistance is equal to 10 kiloohms. The capacitance is equal to 25 nanofarads, and the inductance is equal to 10 henries. With these numbers, we can turn around and start looking at our characteristic equation. So recall from lecture 11 that we have a system where x double dot plus 1 over RC x dot plus 1 over LC times x is equal to 1 over C times the derivative of the input current with respect to t. And where we know that the variable x is just the voltage across the capacitor, which is, by the way, the same voltage as we have in all parts of the circuit, which is kind of convenient. From here, the characteristic equation simply looks like r squared plus 1 over RC times r plus 1 over LC is equal to 0. From that characteristic equation, we know that the roots of this are equal to negative 1/2 of 1 over RC plus or minus 1/2 of the square root of 1 over RC squared minus 4 over LC. If we solve for the first part, and remember we've been calling this alpha, and we've been calling the negative of that times 1/2 beta. So we'll just kind of loosely cover that and talk about what exactly. So if we want to look at the envelope, we're going to look at alpha, and alpha is equal to 1 over 2RC, which is equal to 1 over 2 times 10K times 25 nano. If we take a look at those, then we realize that's equal to 1 over 250 times 2, or 500 micro. But of course, that's just equal to 1 over 0.5 milliseconds. So we know that our system is going to be fairly fast. Now the next thing we're going to look at is beta. Beta is equal to the 1/2 of the square root of 1 over RC squared minus 4 over LC. It's really only the stuff in the square root that we're going to worry about to start with, so let's calculate the stuff that's inside of the square root. We start with 1 over, R is 10K, and C is 25 nano. We're going to need to take that and square it, and then we're going to subtract off 4 over, L is in henries, so that's 10 henries, times C is 25 nanofarads. This is equal to 1 over 250 times 10 to the minus 6, or micro, squared, minus 4 over 250 times 10 to the minus 9. Looking at each of the two individual sides, over here in the denominator we're going to have 2.5, so I'm going to shift that decimal place over, and in order to shift that decimal place over by 2, we're going to have to take it over on the other side. So this is going to be a shift of 2 this way, which means that I'm dividing by 10 to the minus 2, or dividing by 10 to the 2, so I multiply by 10 to the 2. It's 2.5 times 10 to the minus 4 squared. On the other side over here, I'm going to have in the denominator 0.25, that comes from the 1/4 or from the 4 on the top, times 250 times 10 to the minus 9. We shift this one over this way, we shift this one over this way, those cancel, shift this over one more time, that turns into an 8, and lo and behold, these two things are equal. Therefore, this is going to be equal to 0. What that tells us is that for this particular system, the homogeneous solution is critically damped. Therefore, we're going to have a solution that's in the format of C1 times e to the minus t over 2rc. So that's simply, we looked at that already, 2rc is 1 over 0.5 milliseconds plus C2 times time times e to the minus t over 0.5 milliseconds. Notice that you're actually going to need to multiply by 10 to the minus 3 for those milliseconds, but I want to keep this in a format that is easier to see. And this is the homogeneous solution for this system. Notice that homogeneous solution is very fast. After we do this, we go to the next step, and we're going to want to draw our phasors. And at this point, I'm going to leave most of this as an exercise for you and just start you off. In our phasor format, we of course have our standard R, C, and L. Doesn't really matter what order you put them in. And we realize that we started off with 10 at an angle of pi over 6, which is 15 degrees. Sorry, pi over 6 is 30 degrees. And this is at 3 pi radians per second. So we're going to need to take a look at all the other pieces. We know that if R is equal to 10K, this implies that ZR is equal to 10K. Now we know that if C is equal to 25 nanofarads, therefore this implies that Z for the capacitor is equal to negative J over theta, which is 3 pi, times 25 nano. And you're going to take that, divide it out, and get it onto the top. We know that our inductor is equal to 10 Henry, which leads us to an inductive impedance of J times 3 pi times 10. So you take all those pieces, do the standard work in order to get yourself to your phasors, and finish off the problem, finding the phasors for each branch. Recall the things you need to do in order to do this. You're going to need to get your parallel branches. It's very easy to take these two parallel branches first and then take the third one afterwards. That's probably easier than it would be to deal with all three of them all at once, by the way. Once you do that, you want to find ZEQ. That's your first step. Your second step, once you've done that, is to find the voltage across the source, which is equal to the voltage across the resistor, which is equal to the voltage across the capacitor, which is equal to the voltage across the inductor, because they're all in parallel. And that is going to be very easy to do once you have ZEQ, because Vs is equal to Is, we already know what that is, times ZEQ. Now the next step after you've done that is to turn around and work out each of the individual currents. Not a problem to do, because we simply use Ohm's law. We know that for every element, the current is equal to the voltage in that element divided by the impedance in that element. But of course, all of these are the same because it's in parallel. So all you're going to have to do is for each one of these, take IR is equal to V over ZR. IC is equal to V over ZC. And lastly, IL is equal to V over ZL. Once you have all your phasors, you're ready to put your circuit together. So you take your phasors, you can write your equations. Whenever we deal with higher order circuits, we simply follow the 4 steps. So we look for our homogeneous solution, then we find our steady state solution, we put it together, and lastly, we solve for our constants. Solving for the constants in the first order solution system is reasonably easy because we just have to look at the equations directly. As you saw, when you get to higher order circuits, it becomes harder and harder because you have to start looking at the different values of the higher order derivatives in order to get the initial conditions for all of the pieces that you need. So it can be a little bit cumbersome, it's harder to do, but as a process, it's a straightforward process. So at this point, we've got all the tools, we've got examples, and next week we are simply going to have review lectures before the midterm and a take-up midterm lecture after the midterm. So, as you know, the midterm is on Wednesday. The time is from 7 to 9. Same locations as last time. Please check your email on Monday. I'm not sure if you're going to be in the same rooms or if I'm going to change that up a little bit. Thank you very much. Hope you enjoyed the lecture, and I will see you soon.